welcome to this tutorial on TE384 switching in engineering. In the last tutorial, we derived a few formula to calculate the number of cross points for a given switching arrangement. Now in this tutorial, we're going to extend our knowledge and then solve a few examples. So without wasting much time, let's go right into our first example. As you can see on the screen, a 26 channel trunk group is divided into two groups of 13 one-way trunks in each direction. How many lengths of traffic can this system support at 1% blocking? So in the question, we have a 26 channel trunk group, and the question tells us that this system has been divided into two groups of one-way trunks. So we have 13 trunks in each direction. So the first one is asking us how many lengths of traffic can this system support at 1% blocking. So we are going to trace from the Erlang B table with n equals 13 and then our GOS equals 1%. So from the Erlang B table, our offered traffic is equal to 6.607 erlangs. This 6.607 erlangs is for a transmission in one direction. So to find the total traffic, it is going to be twice 6.607 because this is a symmetric system. We have 13 groups in each direction, so it's going to be twice the traffic in one direction. So that gives us 13.214 erlangs. Then the next question is asking us how many erlangs can be supported if all 26 trunks. So all the 26 trunks are being used as two-way trunks at the same 1% blocking. So now from the Erlang B table, we'll do the same thing. Our n is equal to 26. Our GOS is equal to the same 1%. So from the table, our offered traffic is going to be 16.96 erlangs. The next question is for us to find the trunk occupancy. So what is the trunk occupancy in each case? So the trunk occupancy is given by rho, which is the offered traffic intensity times 1 minus the grade of service divided by the number of trunks. Now this is the governing formula to find the trunk occupancy. For a case where you have 0.01 as your grade of service, you are going to realize that it won't have any significant effect on the final answer you're going to get. But for grade of service values above 0.02, if you omit this grade of service value in your calculation, you're going to get a slightly different value. So for the case of the one-way system, or for the case where the 26 trunk groups were grouped into 13 one-way directions, now our A, which was in the previous calculation found to be 13.214. So rho is equal to 13.214 multiplied by 1 minus the grade of service, which is 0.01, all divided by 26, because in total you are going to have 13 in each direction, and so once you add, you are going to have 26. So we are finding a total. This is different from a case where you'll be asked to find them separately for outgoing and then for incoming. But here we are finding the trunk occupancy for the entire system. So we are going to find it using the total traffic intensity and the total number of trunks. And this, once simplified, gives us 0.503 or 50.3%. Then for the two-way system, using the same formula, from our calculation, we had our traffic intensity to be equal to 16.96 erlangs, and it's the same capital N equals 26. So we have 16.96 multiplied by 1 minus 0.01 divided by 26, and we shall have 0.646 as our simplified answer. Now the final question is asking us to determine which of the two systems is more efficient. Now, in comparing the trunk occupancies of two systems, the trunk occupancy is basically a measure of how efficient your system is. So that is to say that the higher the trunk occupancy, the higher the efficiency of the system. And so by comparing, you can see that clearly the both-way system is far more efficient than the one-way system. So you can conclude by saying that the both-way system or the two-way system is more efficient. So we found the supported traffic for both instances, and then we use that to find our trunk occupancies for the two systems. and clearly we can see that the both way system is more efficient. So let's go to the next question. During a busy hour, 9,200 calls were offered to a group of trunks and 72 calls were lost. The average duration is 4 minutes, and we are being asked to find, first of all, the traffic offered, the traffic carried, the grid of service, and the duration of the period of congestion. So let's identify our various parameters. We have 9,200 calls being offered to the group of trunks, and then 72 calls being lost. Then we have our average call duration as 4 minutes. So we have, let's say for instance, N subscript O for offered calls to be 9,200. Then N subscript, let's say L, as our number of lost calls as 72. Then our average holding time, which is H, given by 4 minutes. So to find for the traffic offered, essentially we are going to use the formula A is equal to N subscript O times H all divided by T. And that gives us, if by substituting the values into this formula, we are going to get 9,200 times 4 divided by 60, because we are dealing with minutes, so our observation period is going to be 60 minutes for an hour. So we have our final answer to be 613.33 erlangs. Then our II, our carried traffic, now is going to be the number of offered calls minus the number of lost calls, all multiplied by the average holding time divided by the observation period. So you're going to have 9,200 minus 72 times 4 divided by 60. And for our final answer, we have 608.53 erlangs. So let's turn to the next page to solve the remaining questions. So to find the grade of service, it's essentially given by the offered traffic minus the carried traffic, all divided by the offered traffic, or the lost traffic divided by the offered traffic. So if you substitute the values, you're going to have 613.33 minus 608.53 divided by 613.33, and that gives us 0.0078 for our grade of service. Now the duration of congestion is going to be given by the grade of service multiplied by the observation period, which is 1 hour. But because we have our grade of service in this decimal format, let's normalize this to 60 minutes. So we are going to have our grade of service, or our duration of congestion, being equal to 0.0078 times 60. Effectively, we have 0.468 minutes. So this is quite straightforward. So let's go to the next question. A three-stage switching system is to support capital N equals 1024 inputs and capital N equals 1024 outputs. For 16 first stage and last stage arrays, we have to determine the number of cross points for non-blocking. So we have our capital N value, and then we have our alpha. And since we are dealing with a non-blocking system, the number of cross points is given by the formula N subscript x is equal to 2 times N multiplied by capital K times K multiplying the expression capital N divided by small n all squared. So we need to find the values K and then small n. Now from this problem, our small n is given by capital N divided by alpha. And since we know that capital N is 1024 and then alpha is 16, it means our small n is going to be 64. Then our K is going to be given by the expression 2 times n minus 1. And so we are going to have 2 times 64 minus 1, which gives us 127. And so if we substitute these values into the formula we shall have 2 times 1024 times 127 plus 127 multiplying the expression 1024 divided by our small n, which is 64. 64 all square. And we have our final answer to be 292,608 cross points. So this is another very straightforward question. Let's move on to our next example. Given a switching system which is designed to support 40,000 subscribers during the busy hour, and each subscriber generates an average of 2.0 calls per hour during the busy hour with an average holding time of 45 seconds. What is the offered load to the system? So here we have a system that is designed to support 40,000 subscribers during the busy hour. And each subscriber, so let me just cancel this S. Each subscriber, so it means that one of them generates an average of 2.0 calls per hour during the busy hour with an average holding time of 45 seconds. So to find the offered load, first of all, we have to find the traffic generated per user or per subscriber. And so we are going to use the formula the same NH divided by T. So our small n is 2 calls per hour. So 2 multiplied by the holding time, 45 seconds, times the observation period. Since our holding time is in seconds, our observation period must also be converted to seconds. So that is 3,600. And for that, we are going to have 0.025 erlangs as the traffic intensity generated per user. And so to find the total traffic, we are going to have our capital A given by the number of subscribers times the intensity per user. So we are going to have this 40,000 times 0.025, which gives us 1,000 erlangs. So first we found for the intensity per user, and then we multiplied our answer by the number of subscribers the system is designed to support, and that gives us 1,000 erlangs. So moving on to our next question, question 5. A switching terminal experiences 4 arrivals in a minute. What is the probability that there will be 6 or more arrivals in an arbitrarily chosen 30-second interval? So this is a Poisson model, and for the Poisson system, the probability of having a certain number of arrivals is given by the formula P subscript J of lambda t. Lambda t is basically the number of arrivals in a specific interval. So lambda t to the power j divided by j factorial, or multiplying the expression, the exponential of negative lambda t. So this forms the basis for a Poisson model. By here, we are being asked to find for the instance that we are going to have a certain value greater or equal to j arrivals of the same lambda t. And so by this, it means that we are going to be adding several probabilities. Hence, we have the expression, the summation of I equals j to infinity of p subscript I lambda t, because we have a certain number or more arrivals, and once you have a number or more, it means that it can go up until infinity. And so to simplify this in a way we can easily solve, we can convert this equation such that now we are going to have 1 minus the summation of I equals 0 to j minus 1, because it is greater than or equal to. So once you have the starting point of this expression being j, it means that we can end at j minus 1. So we sum from 0 to j minus 1, and then we subtract the sum of those probabilities from 1. So that then gives us the chance to be able to solve this question. First, we need to find our lambda t, which is essentially the 4 arrivals in a minute times the arbitrarily chosen 30 seconds. So we are finding the number of arrivals you can have within 30 seconds as our average. So we have 30 over 60, and that gives us 2. So our lambda t is 2. So to find the probability of having 6 or more arrivals given a mean arrival of 2, then this is going to be equal to the summation of I equals 6 to positive infinity of the probability of 2 arrivals. And so we can convert this into a formula that looks like this. So we are going to have 1 minus the summation of I equals 0 to 5 pi of 2. So by expanding the summation, then we are going to have, by expanding this expression, we are going to have 1 minus e to the power minus 2, because recalling from this formula, we are going to have our pi of 2 looking like 2 to the power j over j factorial e minus 2. So this exponential of minus 2 will be a constant multiplying the phase values over which we are summing the expression 2 to the power j over j factorial. So we are going to have 1 minus exponential of negative 2 multiplying 2 to the power 0 over 0 factorial plus 2 over 1 factorial plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the power 4 over 4 factorial, and then plus 2 to the power 5 over 5 factorial. And our answer is simplified to be equal to 0.0168 as our probability of having 6 or more curves. Next question. For a 900 by 900 switching system, calculate the number of cross points if the system is achieved using the following configurations. First of all, a full matrix. So this is quite straightforward. So our I, we have our capital N equals 900. So for I, full matrix, the number of cross points is given by n squared. So that is 900 squared. And that gives us 810,000. II, for a folded matrix, the number of cross points is given by the expression n times n minus 1, all divided by 2. And so we're going to have 900 times 900 minus 1 divided by 2. And we shall have for our final answer 404,500. III. We are going to use a two-stage matrix using square matrices as building blocks. And so with this notation in mind, we are going to look for the square root of 900. And that will give us our small n. And so the root of 900 gives us 30. Hence, to find the number of cross points in a two-stage matrix using square matrices as building blocks from our previous tutorial, we found the number of cross points to be given by the formula 2 times n cubed. And so we have the expression 2 times 30 cubed. That gives us 54,000 cross points. So let's go to IV. We are to find the number of cross points if the system is achieved using a three-stage matrix using square matrices as building blocks, including a mixing stage. Additionally, you're supposed to find the overall size of the switch and the number of alternate parts. So we are going to have, for the mixing stage introduced into the system, now our number of cross points is going to be given by the expression 3n cubed. And so we shall have 3 times 30 cubed. That gives us 81,000 cross points. We also have to find the overall size. Now for the mixing stage, once we introduce a mixing stage into a two-stage system, we don't change the size. We are only adding some additional or alternate parts. And so our size is still going to be the same as a normal two-stage network, using the same 30 by 30 as building blocks. And so we shall have n squared by n squared as our size, which is effectively 30 squared by 30 squared. And then we simplify it to 900 by 900. Please take note that in finding the size, we are not trying to multiply the number of inlets by the number of outlets. The size is basically represented by a dimension of how many inlets we have as against how many outlets we have. So 900 by 900. Once you go on to multiply this 900 by 900, you are rather finding the number of cross points in a single stage system, and that is incorrect. Then the number of alternate parts, since it's a mixing stage network, obviously some alternate parts are going to be introduced, and that is always equal to the small n. So we have our number of alternate parts being equal to 30. Then finally, we are supposed to find the number of cross points. Now, if we use a three-stage matrix using the square matrices as building blocks, so now we are going to use the 30 by 30 small matrix to build a three-stage network. So to find the number of cross points, that is given by the formula 3 times n to the power 4. And so we have 3 times 30 to the power 4, simplified to 2,430,000 cross points. Then the overall size of this 3-stage matrix, including the distribution stage, is given by n cubed by n cubed, which is 30 cubed by 30 cubed. You can further simplify to 27,000 by 27,000. And then the number of alternate paths, since it's a distribution network, there is no alternate path added, and so our number of alternate paths is effectively 0. So let's move to the next question. So question 7 reads, a simple junction network has 4 local exchanges A, B, C, and D, and it may also have a tandem exchange T. During the busy hour, each local exchange originates 4.0 erlangs of traffic to each of the others, and the required rate of service is 0.02. We have to determine the number of one-way trunks required in the network if, first of all, direct trunks only are provided. Then, in the second case, when all trunk calls are routed through a tandem exchange. Then finally, we're supposed to find the trunk occupancy between 2 of the exchanges in I, and then between an exchange and a tandem exchange in II. So let's break the question down. First of all, we are told that the junction network has 4 local exchanges. So we have 4 local exchanges, A, B, C, and then D. And each of them generates 4.0 erlangs of traffic to each of the others at a rate of service of 0.02, which is essentially 2%. So the first thing we need to do is to identify the number of routes for the case of the tandem, or for the case of the system without a tandem exchange. The first thing is to identify the number of possible one-way routes, because the question is asking us to find the number of one-way trunks required in the network. So this is what we will do. So for A, remember, they are all connected to each other, or they are all generating some amount of traffic to each other. So essentially, in the simple junction network without a tandem exchange, what happens is that each local exchange has a connection with another local exchange. So for instance, if we take the case of A has a route to B, to C, and then to D. Similarly, B has a route to A, to C, and then to D. And so we use the same principle to fill the table for C and D. So we have C to A. So if you count the number of routes per the table, we're going to have 12 routes in total. So simply put, if we have a system of small n local exchanges, if we want to find the number of one-way routes, so this is 12 one-way routes. If we want to find the number of one-way routes within the network in a simple junction network without a tandem exchange, then it's going to be given by the expression n minus 1 times n, one-way routes. So in the case where we have just 3 local exchanges, then the number of one-way routes in the system without a tandem connection is going to be 3 minus 1 times 3, which gives us 6. So that's formula works for all n values. And so now, after finding the number of one-way routes, which is 12, we go on to find the number of trunks per route. And by that, I mean that if I take, let's say, a connection between B and A, so as B is transmitting to A, from the question, B generates 4 erlangs of traffic to A at a required rate of service of 0.02. So if I check from the erlang B table, I'm going to see that I will need n equals 9 trunks to achieve this transmission. And so this means that we have 9 trunks per route. So effectively, the number of trunks, or the total number of trunks required in the network where only direct trunks are provided, is given by the 9 trunks per route times the 12 routes. And so we have 108 trunks in this system. Similarly, for the system with a tandem exchange, now if you have a tandem exchange in the network, what it means is that the tandem exchange is central to all the local exchanges. So we have A, B, C, and D. So the tandem exchange controls all the routing process. So it receives traffic from A and then forwards it to C, D, and B. Similarly, if it receives traffic from B, it forwards them to A, C, and D, because the question says they generate some amount of traffic to each other. But one thing of note in this operation is that if A is to transmit, for instance, X amount of traffic to each of C, B, and then D, what it means is that it will transmit 3x to T, and then T will forward the X, or 1/3 of 3x, to each of B, D, and C. And so in a numerical example, for instance, in this case, if A wants to generate or originate 4 erlangs to each of B, C, and D, here we are going to have 3 times 4 erlangs, which is 12. And so once the 12 erlangs get into the tandem exchange, the tandem will forward 4 erlangs to B, 4 erlangs to D, and then 4 erlangs to C. And so this is the basic operating principle or operation principle of the tandem exchange. So let's look at the number of routes in this system, the number of one-way routes in this system. So we have our table A, B, C, D. Remember, we're dealing with one-way routes, so we shall have A to T, and then T to A, B to T, T to B, C to T, T to C, and then finally D to T, and T to D. So you can see from the table that we have 8 one-way routes in the system that contains the tandem exchange. So 8 one-way routes. Then we go on to find the number of trunks per route, and then that will help us find the total number of trunks in the system. So the number of one-way trunks per route. Let's take, for instance, the connection between A and T. Taking note of the operation principle of the tandem exchange, we can see that if A is originating some amount of traffic to T, in order to have a communication or amount of traffic generated to each of B, D, and C, A will generate 3 times the traffic cited in the question. So A will generate 12 erlangs to T. So this 12 erlangs at 0.02 blocking, we are going to need N equals 19 trunks. And so we have 19 trunks per route. So the total number of one-way trunks in this system is going to be given by the expression 8 times 19, which gives us 152 trunks. So one important observation about this type of problem is that you are going to need more trunks in the tandem system than in the simple junction network that has no tandem exchange. And the final question is asking us to find the trunk occupancy between two of the exchanges in the case where we have no tandem exchange, and then in another case where we have a tandem exchange. And particularly, you're supposed to find the trunk occupancy between an exchange and the tandem exchange. And so in the case of the network that has no tandem exchange, our trunk occupancy, which is given by rho, as always, the formula 1 minus the grade of service divided by the number of trunks. Now if you go back to check, you would see that between a pair of exchanges, now there are going to be 2 of the one-way transmissions. So as B originates 4 erlangs to A, A will also originate 4 erlangs to B. So in total, you can see that we have 8 erlangs being transmitted in the connection. Then for the number of trunks, as B transmits 4 erlangs to A at 0.02, needing 9 trunks, A will similarly transmit 4 erlangs at 0.02, needing 9 trunks. And so we are going to have 18 trunks in the entire system, or in the pair of exchanges. So we are going to have 8 times 1 minus 0.02 divided by our 18 trunks, which gives us 0.44 or 44%. Similarly, in the case where we have a tandem exchange, so let's say between T and then A, A will originate in practice 12 lengths to T, and similarly T will accumulate the traffic coming from B, D, and C and also send them to A. And so as A is transmitting 12 lengths to T, T will transmit 12 lengths in the opposite direction to A. And so we are going to have our total traffic intensity being 24. So rho is equal to 24 divided by 1 minus our GOS, which is 0.02. Now let's see the number of trunks we are going to need in total. We had 19 trunks to support the 12 lengths A will generate to T or originate to T. So similarly, T will also need 19 trunks to originate some amount of traffic, which is 12 lengths to T. So in total we have 38 trunks. And so if we simplify this expression, we are going to see that we are going to have 62% or 0.62. So from observing the trunk occupancies of the system without a tandem exchange and the one with a tandem exchange, you can see that clearly the tandem exchange system is much more efficient compared to the junction network without a tandem exchange. So finally, our last question. A central office to PBX trunk group contains 5 circuits. If the average call duration is 3 minutes and the busy hour offered traffic is 2.5 lengths, we are asked to find first of all the busy hour calling rate, the blocking probability assuming the lost calls cleared operation, and the amount of lost traffic. So we have 5 circuits that represents our capital N, and then our H being 3 minutes, and then our busy hour offered traffic intensity being equal to 2.5 lengths. So the first question, to find the busy hour calling rates, which is small n, using the formula A equals NH over T, we can see that N is equal to A times T divided by H. And so you're going to have 2.5 times 60 divided by 3, giving us 50 calls per hour. So to find the blocking probability, it is given by the expression B into bracket NA, giving us A to the power N divided by N factorial, multiplying the summation of K equals 0 to N, A to the power K over K factorial. So if we input the various values, or if we do our substitution, we're going to have B of our N, which was 5, and then our A, which was 2.5. So 5, 2.5. Then let's substitute. So we're going to have 2.5 to the power 5 divided by 5 factorial summation. So we're going to have 2.5 to the power 0 divided by 0 factorial, 2.5 to the power 1 divided by 1 factorial, 2.5 to the power 2 divided by 2 factorial, 2.5 to the power 3 divided by 3 factorial, 2.5 to the power 4 divided by 4 factorial, and finally 2.5 to the power 5 divided by 5 factorial. Once we simplify, we're going to get our grid of service or the blocking probability to be equal to 0.0697. Then the last question is asking us to find the amount of lost traffic. By using the relation, our grid of service equals the lost traffic divided by the offered traffic. You can see that our lost traffic is going to be equal to the grid of service times our offered traffic. Our offered traffic from the question was 2.5 lengths, and then our grid of service was 0.0697. So 0.0697 times 2.5. So that gives us 0.174 lengths. So in effect, we've been able to solve this question, which is also quite straightforward. So conclusively, today we've been able to try various examples ranging from teletraffic analysis to switching systems using smaller blocks to achieve a certain configuration. And then we've also essentially tried to prove that both-way trunk groups are more efficient than one-way trunk groups. So thank you very much for your attention, and I wish you the best in your exams. Bye.